Hey guys, Miss Alfred here. I'm going to try to do a quick review of geology and plate tectonics. So minerals and rocks were covered in a different video, but we're going to be talking more about the larger scale geology and plate tectonics. So first of all, plate tectonics. When we look at Earth structure, we have the atmosphere, obviously outside. You have the crust, and then the mantle, the outer core, and the inner core. The crust is that hardened rock. It has solidified and it broke into plates, which we didn't always know. Oceanic crust is very, very thin. Continental crust is much thicker. And then you have the mantle, which is actually molten. It goes up and down in a circular pattern, convection currents, because down here it's getting heated by the outer core. So that molten rock gets heated here along the core. It becomes less dense, it rises towards the surface, it cools, and then it actually sinks because it becomes more dense, and this continues to happen. The outer core is molten metal, and the inner core is solid metal from Earth's gravity. So this theory of plate tectonics, and actually what was called continental drift, was developed by Alfred Wegener, and he was he was German, and he kept looking at the fossil record and saying, we got fossils on different continents. The continents kind of look like puzzle pieces. And so I have a feeling that at one point, all of the continents on Earth were all together and eventually got pushed apart. And of course, he was ridiculed, laughed at, just actually ended up having to go teach meteorology for the rest of his life because everyone thought this was ridiculous. Because how did the continents move? What, did they just have a bad breakup and decide to go their separate ways? Obviously not the case. It wasn't until he died in the 1930s, it wasn't until the 60s as we started getting down into the deep ocean that we started figuring out, hey, wait a minute, he was onto something. It really is changing down there. So Harry Haas later was the one who found seafloor spreading, and now of course we know there are convection currents that are happening in the mantle, and that is what is moving the plates. Okay, so our plate boundaries can be one of several things. They can be divergent, where they move away from each other. Okay, convergent, where they're going towards each other, or transform, going side to side, like the San Andreas Fault. And each one of these creates different different structures on the surface that we can identify. So the mid-ocean ridge is the thinnest and youngest. This is brand new baby rock that has formed from magma rising to the surface and cooling. And we get what's called seafloor spreading, where as these plates move apart, you end up with magma coming up and cooling, and it forms a ridge. And so it's very, very thin right through there, obviously. And as it continues to move, it's actually pushing the different continents in different directions. In convergent plate boundaries, in a continent-to-continent situation, those two continents running into each other have nowhere to go. Neither one of them is going to give, neither one of them is going to sink. So in fact, what they do is they crash into each other and they form these big folded mountains. And so a great example of that is the Himalayas, where you have the Indian plate that has crashed into the Asian plate. You can also have continent to ocean, and again, if you have continental crust and oceanic crust and they run into each other, that oceanic crust is going to actually slip down underneath. And this is not an easy process, obviously. It makes it a lot easier with your hands than it is with huge plates of the Earth's crust. So we end up with a lot of earthquakes happening here. You end up with a trench that is created, a subduction zone where this is getting subducted or sucked down under, and then this melts. And because of that melting, all that heat, all that pressure, all that melting of oceanic crust, we end up finding volcanoes inland. And so this is what we see on the West Coast around the Ring of Fire, specifically some concerns about what might happen to Seattle or other parts of the West Coast, because you do have some volcanoes inland, and we do have some evidence that subduction's been occurring there for thousands of years. But in the event of a major shift in that deep ocean trench, and the potential tsunami and what impact that would have for people living in the coastal area. So typically this is going to be our oldest areas, and the trench are very, very deep. Okay. In an ocean-to-ocean subduction situation, again, two pieces of oceanic crust running into each other, one of them is going to slip down under. And you still have a lot of heat, you still have a lot of pressure, you still have a lot of melting, which ends up also creating volcanoes, but these volcanoes end up forming an ocean arc. They're not inside the continent, they're out in the middle of the ocean, and you'll find a chain of volcanic islands where this is occurring. There are some in the South Pacific that are precisely this way. Oh, skipped one. Okay, so earthquakes and faulting. So you have faults, typically along plate boundaries, but we also have faults in other parts of the Earth's surface where the land itself is under pressure, and so it cracks, it breaks. And so when an earthquake happens, it's typically across one of these fault things. Now, the piece that looks like you could draw a shoe on it, okay, like your ankle would be here, you could draw shoelaces down here, this would be the sole of the foot. This is in fact called the footwall. And the other piece, which is like an upside down shoe, is the hanging wall. And depending on the type of fault, you're going to have different placement of the hanging wall in relation to the footwall. So in a normal fault, what's happening is that these two pieces are being pulled apart, and as such the hanging wall slips down. This is tension. The force is tension because they're getting pulled apart, and so they are diverging, and again you find that hanging wall slipping downwards. In a reverse fault where you have compression, these are getting pushed together, and so the hanging wall slips up. Okay, it actually gets pushed up and over the footwall. In a strike-slip fault, these are moving in two different directions, not towards each other, not away from each other. So oftentimes we don't have a defined footwall versus hanging wall, but we do get a lot of earthquakes here. So this is what's happening in the San Andreas Fault in Southern California, which is why we have so many earthquakes there. And this is shearing. It's called a transform fault. Okay. So when an earthquake happens, the rock doesn't break up here on the surface, it actually breaks deep underground, and that's called the focus. Okay, that's actually where the break happens, and that's where all the energy is radiating outward from. However, there's generally a location on the surface, which we call the epicenter, and the epicenter is the place on the surface where it appears that the earthquake is coming from. So the East Coast earthquake we had a couple of years ago was the epicenter was right in Mineral, Virginia, which is in Louisa County, and it appeared to be going outwards from there. Okay, primary waves are the fastest. They're the first waves to arrive, and it's like pushing. Remember I talked about that slinky? So if you're standing here and all of a sudden you get primary waves, the ground is going to be moving under your feet away from the epicenter. Okay, you can see those waves moving outward. It is compression. Secondary waves don't go actually through liquids. Sorry about that. And they actually go side to side. Okay, so you get horizontal movement, and this can do a significant amount of damage. Surface waves, on the other hand, that's these ones right here, and they can do a lot of damage. These waves go up and down in a vertical motion. So in the event you're ever somewhere with an earthquake, you want to be calm, you want to get out of the building, you want to get away from the building because you don't want to be anywhere near the building if it should collapse due to the surface waves. Those ones are big time. So if you feel the primary waves, go ahead, stay calm, get out of the building, and then try to get somewhere where it's going to be safe. Okay, to locate the epicenter, the seismograph is the machine that measures earthquake waves, and you can use ones in different areas. So in this case, you have a seismograph in Pittsburgh that picks up an earthquake approximately this distance away. You have one in New York City that picks up on one this distance away, and you have one in New Orleans which picks up on an earthquake this distance away. Where those three circles collide, that's going to be your epicenter, most likely where it happened. Okay, talking about rocks and looking at geologic time and how long we've looked at geology. Superposition. The rock layer on the bottom is typically the oldest, and the layers get younger as you move up. Any undisturbed rock exposure, that's going to be the case. Igneous intrusions is where magma gets injected across rock layers in the crust, and igneous intrusions are always younger than the rock they're found in. Igneous extrusion, this is where lava actually erupted onto the surface and cooled. So it's younger than the layers below it, even though it came through them. And you may find contact metamorphic rock, where as that magma came through, it kind of crystallized the existing rock around it. Folds or bends in the rock layers, they always happen after the rock layers formed. Faults, that's the cracks where some movement has taken place. And so you get offset layers because that hanging wall either slipping down or getting pushed up. And an unconformity is a buried erosion surface. So at some point it was eroded and then more rock has been placed on top of it, more sediment. So looking at geologic time, fossils are the remains of evidence of former living things. Could be any number of these, typically found in sedimentary rock. Igneous rock, the lava would have burned anything up that would have produced a fossil, and in metamorphic rock, that heat and pressure has typically destroyed any fossils that would have been there. Okay, a mold, the impression made by a fossil, it's typically hollow. A cast is formed when a mold is filled in. Carbon films, you end up with a little bit of carbon that remains in the specimen. Petrified, this is when minerals seep into and slowly replace the organic tissues. So this often happens with wood. We don't have fossilized wood so much as it is petrified wood, petrified trees. And trace fossils, these are really important. Trace fossils are ones that show us that living things were once there. So these are things like footprints or fossilized dinosaur poop. It's not necessarily the dinosaur, it's not necessarily its bones, but it tells us that the dinosaur at one point was living in that area. Okay, so index fossils are used to find the age of the rock in which it was found. Index fossils are things that survive for a very small period of time, but in a large place all around the earth. And therefore, when we find them, we know anything below that is typically older, anything above that is going to be more recent. Okay, so here we have a fault, and you also have a rock profile. You can see our key over here of limestone, sandstone, shale, basalt, and any contact metamorphism is going to be indicated with this. So what we have here is some limestone, and above that was shale, and above that was sandstone, and then we ended up with more limestone. These were all laid, and they were nice and flat and orderly, and everything looked great. Then there was some faulting that took place, okay, where that was put under some tension, and the hanging wall has slipped down. But at some point after that, even more recently, you've had some magma that has seeped through these rock layers, and as such, it has formed basalt. Okay, absolute dating of rocks, we look at radioactive isotopes of different elements to see how long it takes them to degrade. These isotopes have a slightly higher mass, and they're not very stable. They don't like to be that way, and so they decay at a steady rate. So relative dating is the law of superposition. The one on the bottom is the oldest, the one on the top is the youngest. Okay? And our geologic time scale is based on life forms that were existing. So during our Precambrian period, we had cyanobacteria, those teal bacteria that actually release oxygen as a byproduct, and that helped to form our early atmosphere. Beyond that, we have the Paleozoic, where we start to see some fish, we start to see some vertebrates, and we start to see some trees. Beyond that, we get into the Mesozoic, and this is where we had our dinosaurs. The Cenozoic is our current era, and the Cenozoic is where we have the development of mammals and eventually of humans. Okay, so let's talk specifically about Virginia geology, and this is going to be fast. We have the Appalachian Plateau, the Valley and Ridge, the Blue Ridge, the Piedmont, and the Coastal Plain. The Appalachian Plateau, this is where we find coal, and so that is going to be the remains of ancient swamps or shallow water areas. The Valley and Ridge area, we find a lot of limestone, so again, ancient coral reefs. We've got Blue Ridge, which is mainly igneous and metamorphic rock, a lot of folding, so we don't see a lot of fossils here. And in the Piedmont region, we end up with a lot of sedimentary rock. Our coastal plain is the youngest part of the state, and it's still a lot of sedimentary rock is forming here. Okay, so you could look even more clearly at just the coastal plain and take a look at those different things and when they were formed, and that's it. Thanks, guys.